All right, everyone, let's begin the section of this course that deals with something called infinite series. And the first lesson is not too bad at all. It deals with something prior to series called a sequence. So this is an intro to sequences. And I've started you off right here with a sequence. So a sequence is basically just a list of numbers that are generated using some kind of mathematical rule or some kind of mathematical pattern. So if you look at this one, we have brackets indicating like it's one of these special curly brackets, meaning it's a list of numbers. And we have this sequence of numbers 1, 2, 4, 8, 16, dot, dot, dot. The dot, dot, dot means it's an infinite sequence. It goes on and on. It does not have a last term. So that idea of a last term is going to be pretty important. So when you see a sequence, that just is a list of numbers generated by a mathematical rule. So list of numbers generated by a rule. Let's say rule, a mathematical rule though. So you can talk about it and say, okay, well, the first term is 1, and then if we just double each term, that's how you would get the next term of the sequence. But we'd rather talk about this using a mathematical rule. So one way to do it is like this. You say, okay, to generate the sequence, we're going to call the sequence A. To get any number of the sequence, we would use this pattern right here. So this is called the explicit formula for this sequence above. And you can see how it works. If I plugged in 1, you get 2 to the 1 minus 1, which is 0. 2 to the 0 is 1, which generated the first term of the sequence. If you plugged in 2, you plug in 2, you get 2 to the first, which is 2. If you plugged in like 5, you get 2 to the fourth, which is 16. That would give you the fifth term of the sequence, which is 16. So we're going to be typically dealing with sequences and series that are defined like this explicitly. There is another way to talk about sequences called recursively. I'm not even going to bring it up this year. It never pops up. But basically, you're given the first term and the rule to get the next term, and then you use the next term to get the next term and so on, kind of like Euler's method. But we don't really need to know about that in this part of the course. All we care about is the explicit form for finding a sequence. So there it is. So let's look at some examples of various sequences that will be popping up. Here are some examples. We already saw the first one. Here's another one. And we don't have to use A. We typically do, though. So here's the sequence of A sub n. And I want to do this one. 3 plus negative 1 to the n. Now you're going to hear me say this a lot. Expand out the sequence when you're trying to figure things out about it. So that just means write it out term by term by term by term until you can kind of get a handle on what's going on. So let's do just that. Let's plug in 1 to get the first term. We'd have 3 plus negative 1 to the first power. Negative 1 to the first is just negative 1. So 3 minus 1 is 2. The next term would be when you plug in a 2, you get a positive 1 because when you square a number, it makes a positive. And 3 plus 1 is 4. And then you plug in 3 and you get a negative 1 again, and that would be back to 2. And then 4. And then 2. And then 4. On and on and on. So this is kind of cool. It's called an alternating sequence where the terms alternate back and forth. It's a pretty common one that's going to pop up. And there's a first example. Here's another sequence. We'll call this one B sub n. Just like functions, how we can have f and g and h with sequences or series, we can have a or b or anything. Typically, it's a and b. The next one, how about just 3 to the n? This is going to be an important one. It's called a geometric sequence for reasons that will come up later. Plug in 1, you get 3. Plug in 2, you get 9. Plug in 3, you get 27. Plug in 4, you get 81. Plug in 5, 243, and so on and so forth. Cool. So there's a sequence that is generated by this rule, which basically just says powers of 3. One more. Something like this. This is another geometric for reasons we'll talk about later. 1/5 to the n. So we plug in 1, we get 1/5. We plug in 2, we get 1/25. We plug in 3, we get 1 over 125. On and on and on. How many terms should you write out? I don't know. It depends on the problem. Typically, it's 4. So a lot of times we'll say find the first 4 terms of the whatever, and we'll be dealing with 4 terms. So these are examples of some sequences. Now, what are we supposed to do with these? Not a whole lot right now. This is just an introduction to sequences and the notation. But ideally, the goal of this first section is very, very, very important, leading into other things. And the goal is this. The goal is to determine if the sequence, and here's our key word, converges to a value or diverges. So we saw this a little bit with improper integrals. That's the key of this whole first section. We don't even really care about the sequence of numbers. All we really care about is if the sequence converges to a value, converges to a value, or diverges. So there are ways to figure this out, and that's going to be what we're doing for a while early on. And what I mean by converges to a value, I kind of mean this in a very, very, very informal way. I'm basically just saying, is there a last term that we're getting closer and closer to? You'll see what I mean as we do more examples, but let me show you with these first 3 that we've done. So if you look at this sequence, 2 and then 4 and then 2 and then 4 and then 2 and then 4. Does it look like we're getting closer and closer and closer to any term? No, we're oscillating back and forth. So this is an example of a sequence that diverges. There is no last term. It's either 2 or 4 back and forth, and we're never going to end on either one of those. We're just going to keep going back and forth between 2 and 4. This next one definitely is not going back and forth. It's just getting bigger and bigger and bigger and bigger. So when you have a sequence that just gets bigger and bigger and bigger and bigger, that also diverges. So it goes to infinity. Don't say converges to infinity. If it goes to infinity, we say it diverges. How about this last one, though? This one's a little unique. The first was 1/5. Then we get a smaller term and an even smaller term and an even smaller term and an even smaller term if we were to keep going. This one does actually converge. What value are we getting closer and closer and closer to? Well, we're getting closer and closer to 0. This is an example of a sequence that converges to 0. So how are we supposed to determine if sequences converge? Well, you may already start to have an idea, but let's look at an example of a different sequence and see if we can find a really nice shortcut. So here we go. We have 3n plus 1 over n minus 2. Here is a sequence. You may think this just looks like a normal function. Looks like a rational function. Yeah, these are very similar to functions, except you only plug in whole number values. So we don't deal with decimals. So this generates a sequence that looks like the following. If you plugged in 1, you'd get 4 over 1 minus 2 is negative 1. If you plugged in 2, you'd get 7 over, that's kind of about. Let's change it to plus. Sorry, sometimes I do this. Change it to plus, that way it works out. So going back, we plug in 1, we get 4/3. Plug in 2, 7/4. Plug in 3, plug in 3, we get 10 over 5, which is 2. Plug in 4, we get, well, these keep increasing by 3 and these keep increasing by 1, so 13 over 6. The next one would be 16 over 7, and on and on and on. So look at this one. You're like, well, it's getting bigger and bigger and bigger. So does this one diverge? Well, it's getting bigger and bigger, but at a smaller rate. Like this first one is 1 1/3, and then slightly less than 2, and then 2, and then barely bigger than 2, and then even small. Like the distance between them is getting smaller and smaller. So if I were to ask you, is there a last term, which is the same question as does this sequence converge or diverge? It turns out this one converges. There is a last term. If I were to have you write out the first 100 terms, which I'm not going to do, you would see that the last term is super, super, super close to something. And it turns out that this one, in fact, converges to, drumroll, 3. How did I do that so quickly? Well, we're already set up to do this. We are going to essentially just look at the limit as n approaches infinity of the sequence. So you just got to know your end behavior rules when you're doing these types of problems. So if I were to say, okay, what is the limit as n approaches infinity of 3n plus 1 over n plus 2? We go to the powers. We notice, oh, look, the powers are the same in the numerator and denominator. That means divide the coefficients, and lo and behold, 3 divided by 1 is 3. So that is how we are going to figure out if sequences converge or diverge. We're just going to look at the end behavior. So for example, in this first one, a little bit trickier, so we won't look at that one, but look at the next one. The end behavior of this, 3 to infinity, is infinity. So that's why it diverged, didn't get smaller. This one, you have 1 to the n over 5 to the n. So in this case, you can't look at the leading coefficient. You got to kind of look at it this way. You have 1 to the n, which is just 1 over 5 to the n. 1 to the n is just 1, but 5 to the n grows way faster than 1 to the n. It's almost like a squared power and a fourth power in the bottom. The bottom is bigger growing or faster growing than the top, so this was why this one converges to 0. So that's what we're doing in this first section. I give you a sequence like the following, and you tell me if it converges or diverges. And if it converges, you tell me what it converges to. So here's a sequence. We don't even have to write it out. All I care about is, does it converge or diverge? So converge or diverge. So rather than write out the sequence, we can just talk about the limit as n approaches infinity and use our end behavior rules. And notice, again, same power in the top and bottom. So we divide the leading coefficients and we get -1/2. So this sequence converges to -1/2. The quote-unquote last term would be -1/2. So it doesn't seem so bad. It seems like we're just dealing with end behavior. The trickiness comes in a little bit when we have a mix of functions. I'm going to call it functions because they are, even though we're only plugging in whole number values. But when you start to have a mix of functions, now things get a little more interesting. So what about one like this? We have an n plus 1 on top, and we have a 3 to the n on the bottom. And I will ask the question, does this sequence converge or diverge? Well, this is where you need to know something called the growth rate of functions and how they compare. And I've talked about this a little bit in class already, but you need to understand that, okay, the top is linear, or first degree. The bottom's exponential with a base of 3. So exponentials grow way faster than linears. So in this case, the bottom grows faster than the top. And when that happens, that means the end behavior is 0. So this is a sequence that converges to 0. So there is an order of functions that you need to know, and I'm going to write it right here. So the growth rate of functions, and I ask about this in the homework, so make sure you have this down. We're going to need this desperately when we are doing these types of problems. So the growth rate of functions, here we go. Slowest growing functions we have, constant doesn't really count because it doesn't grow. So the slowest growing are your logarithmic functions. And people always at this point say, oh, and the natural log. Well, the natural log is a type of log function. So the bigger the base, the slower growing it is. So log base like 10 is super slow growing compared to like log base 3, which grows a little faster. Natural log is a little bit less because natural log is just log base e, which is 2.7, and then like log base 2. Okay, so the bigger the base on the log, the slower growing it is. So logs grow super slow. Okay, after the logs come your radical or fractional powers. So I'll just say that your radical functions. And this kind of follows the same idea. So a square root is probably the fastest growing of the radicals. The bigger the root, the slower growing it is. So if you have a 10th root, that's less than a cube root, which is less than a square root. Because like, okay, the cube root of a number is way smaller than the square root of that number. So similar with logs, the bigger the type of radical, the slower growing it is. After radicals, then we get to our linears, which is just, x or n. And then any number in front, 2n, 3n, 5n, 10n. Linear is the next quickest growing function. After linear, we get into our polynomial. And that would be something like n squared, n cubed. Oops, I should do this. The bigger the power, the faster growing it is. So n to the 7th, n to the 15th. Dang it. So the bigger the power, the faster growing. After the polynomials, then we get into the exponentials. Okay, so this is where you got to pay attention. Because exponentials, you're going to think the coefficient's different, but they're not. The exponential base is part of the function. So for example, 2 to the n is slower growing than e to the n, which is slower growing than 5 to the n, which is slower growing than 7 to the n, and that same kind of pattern. That's confusing for students because they look at back to the polynomial world and they think like, oh, 2n squared and 7n squared. Well, then 7n squared is faster growing. No, they grow at the same rate. This one is just by a factor of 7 that all of its outputs are going to be bigger than the factor of 2 on this one. But they grow at the same rate. If you graph 2n squared and 7n squared, they grow in a similar portion to each other. It's just they're off by a coefficient. Whereas in these cases, 5 to the n is a different exponential base. It grows way faster, and its growth rate increases more rapidly than e to the n. So just remember, on these ones, 2 and 7 are coefficients. The function itself is n squared and n squared, same growth rate at infinity. In these ones, 2 to the n and 5 to the n are two different functions, where 5 to the n is a faster growing function than 2 to the n. We will see that a lot as we go forward. And finally, the last type that we're not going to see for a little bit is called factorial. So when you have a function that's factorial, and we're really only going to see n factorial. Same logic though, if I throw a 5 next to this inside of the factorial, that's going to go faster. So if you've never seen factorial before, factorial just means this. 5 factorial, the number 5 factorial is 5 times 4 times 3 times 2 times 1. And then you just multiply it together and you get 120. So 5 factorial means take 5 and multiply it by all of the whole numbers that are less than it, up to 1. And we see factorials now because we're dealing with whole number inputs. When we had decimals, factorials don't make sense exactly, at least the way we use them here. But you can plug a whole number factorial, and it just means multiply by every subsequent number smaller. So this is our growth rate that's going to be super important for everything, because I'm going to ask you questions like this. Determine if the following converges or diverges. Ready? A sub n equals n factorial over 200 to the nth power. There's no work to do. You just have to know your order of growth rates. So if you look at this, factorial is the fastest growing. So as long as the bottom is not a factorial, this sequence is going to diverge, and it is. The top is faster at infinity than the bottom. Factorials grow faster than exponentials. Now, if you were to try to test this in Desmos and plugged in 1, you get 1 over 200. And you're like, okay. And you plug in 2, you'd get 2 over 200 squared, which is even closer to 0. And you're like, what are you talking about, Mr. West? This thing is definitely getting closer and closer to 0. Yeah, early on. But if you plugged in 1,000 factorial is way bigger than 200 to the 1,000th power. So 1,000 factorial, way bigger than 200 to the 1,000th. Here's why. 200 to the 1,000th is 200 times itself 1,000 times. 1,000 factorial is 1,000 times 999 times 998 times 997, on and on and on. Look at how many bigger numbers we have in this top one as opposed to this bottom one. So, yes, factorial, once you go to infinity, is faster growing, for sure. Okay, so the idea here is, can you look at the growth rates and compare them? So, not too bad. One more thing we got to talk about is, technically 2 more things. 2 special cases and we're done. if we have cosine n over n, what on earth is going on here then? Does this sequence converge or diverge? Well, think about if you were to plug values into cosine. It doesn't have to be radians. It could just be any value. Cosine just fluctuates between -1 and 1, so it doesn't really grow. It just bounces back and forth between -1 and 1. So when you see a cosine or sine, just think, oh, that's not even growing. It's almost like it's constant. It's just going back and forth between values of -1 and 1. So really, you can just look at it and compare it to this series instead. And 1 over n, does this sequence converge or diverge? Well, top's not growing, but the bottom is, so this converges to 0. Not 0 factorial, 0. 0 factorial is 1, by the way, if that ever pops up, and it will. So it converges to 0. I guess I should get rid of that. 0 factorial is 1, though, believe it or not. And then one other case, what about ones that look a little bit trickier, like this, n equals e to the negative n? You're like, oh, I don't like negative exponents. Neither do I. So we saw a trick when we were dealing with improper integrals, and this trick is super important. Move it to the bottom. And now compare growth rates. Well, the top is linear, the bottom is exponential, so this also converges to 0. So this doesn't seem super exciting. We're always getting values of 0 or diverges. Yeah, when you have a mix of functions, typically you are going to get 0 or infinity. But after this section, you're going to see that most of the time we actually end up getting 0, because everything we do hinges on the fact that the sequence is going to have to converge to 0. If the sequence doesn't converge to 0, it's not a helpful sequence to work with for things we're going to be doing later. So most of the time, you're just confirming that the sequence converges to 0, and then we move on and do other things. So get used to this happening a lot. So the growth rate is pretty important. And then just remembering to do end behavior, and remember a sequence is just a list of numbers generated by some mathematical rule, and we just care about the last term, or what the sequence converges to, or if it diverges. All right, and that is it for now. Bye-bye.